Good Monday morning. Today, our agenda will be dam, unforced vibration, and we are going to do some examples. Okay. More important, I have to reschedule term test 1 because there's a major conflict with the math department, which I decided to move our term test because that class has 600 students, and it's only right that we move, okay? Not that I'm a loser. Are we clear? Okay. So I have 3 dates that I'd like to propose. October the 1st, which is, I think it's a Tuesday. October the 2nd, which is a Wednesday. And then October the 4th on the Friday. I'd like you to raise your hand who cannot or who has a term test scheduled on Tuesday, 6 or Tuesday on 6:30 to 9 o'clock. Who has a term test on that day? Again, you have a? Is it a term test? If it's a term test, then is I have to consider. If it's a tutorial, if you could. Hey, yeah, could you a what? Okay, so I have one conflict. The first, how about the Wednesday? Oh, Wednesday, what conflict you have on Wednesday? Oh, that is the one. I'm sorry. I got it. Sorry. Oh, yeah, that's the one that make me move. So that is on the 2nd, right? Am I right? Okay, so sorry. How many have conflict on the 3rd? What is it? Oh, who teaches that? Oh, okay, yeah, I remember. On the 4th, calling once, calling twice. Okay, we have set our term test 1 on the 4th of October. Okay, yes. How many of you have conflict on the 2nd midterm? I can do something for you, okay? If it's just one person, if it's like a lot. So the term test will be on the 4th, okay, which is on a Friday, 6:30 to 9 p.m. And you're going to have 3 long questions, okay? Okay, at least that is sorted out. I like your being proactive, okay? I received close to like 20 emails telling me there's a conflict and there's conflict. And the prof also contact me. You have to move, okay? So there's a conflict. I decided to move. Right. I'm happy now. Are you happy or no? Yes? Good, okay? So we are going to look into a dam. Unforced. And sometimes the term that we tend to use is free vibration, okay, or mechanical system. So we are going to look at some 3 examples. So what if now we have a system over here? Or before I go on, last week we talked about, or on Thursday, we mentioned about different systems or response. We have 3 cases, which I will go through, okay? So that's where I'm going to start from, okay? So if we were to look at a dam, okay, so we have a spring, we have a damper. No, damper don't look like that, Eugene. A damper. Okay. So initially, this is our system. Okay. So you have a K and you have a C. Okay. So just to quickly recall, K is your spring stiffness. And C is your damping coefficient. So in this system, what we have is we are going to hang a load. So when you hang a load, what tend to happen is the spring tend to extend and the damper tend to change in length also. So I deliberately draw this longer, as you can see, and this is we put a mass at this end, and this is K, and this is our C. Any idea why the spring and damper position move? It's because of what? It's because of the weight. Yes or no? Right? The extension. So if I call this our distance here to here, this is Y1, and now this is our what? Y2. So our Y2 minus Y1 is not equal to what? 0. Okay, so this is due to the weight of the mass. Okay. So from here, we are going to put some values. Okay. So the mass that we're going to consider now is 9.072 kilogram. It's just arbitrary numbers. There's no reason why I picked that. Okay. Our C now, damping coefficient, we are running at 200 Newton per meter second. Or no, 200, no, Newton second per meter. And then we have a spring stiffness of 700 Newton per meter. Okay. So our mechanical system have a mass, damping coefficient, and also we have a spring stiffness. Now, this is followed by our boundary condition. So our boundary condition, we specify when time is equal to 0 seconds. So basically, this is the initial boundary condition. We have our Y distance is equal to 0.15 meters. And then our Y dot velocity is equal to 0 meters per second. And this corresponds to dy over dt. At the same time, okay, I'll let you guys finish copying first. At the same time, we declare that y positive is coming downwards. Okay, we made that declaration. If you were to declare otherwise, if you were to declare that over here, right, if y minus is coming down, then your boundary condition has to what? Has to change likewise. Okay. So from here, we have to now, we are capable of forming our characteristic equations. Okay. So it's a general form of our equation. Okay. Just to sidetrack, y characteristic. Characteristic come from what word? Originate from what word? Character, yes or no? So why we call it characteristic equation? I'll tell you about me. I'm impatient. Sometimes can be really sarcastic. And I think I need anger management. Why is that? My character. Are we clear? So the character of the system, be mindful of your character, okay? So you know you're working on it. Don't think that you are perfect. I'm not, okay? So I'm impatient, can be really sarcastic at time, and I need anger management. Okay. So now, looking at here, the mass is a character of the system, yes or no? The stiffness is a character of the system, and the damping is also the character of a system. Okay. So from here, we know that the characteristic equation comprises of m squared y over dt squared plus by c dy by dt and plus by ky, and the whole thing is equal to 0. As you know that if the whole thing is equal to 0 is because of unforced, or another term that textbook tend to use is free vibration. So depending on what textbook you read, you will see this term, okay? So we are aware that we have to, so what we're going to do, we're going to apply what we learned last week, right? So we know that we have to calculate, okay, two things. Alpha, which is equal to C over 2m, and we have to calculate beta, which is equal to what? C squared minus 4mk, and then on the square root, and then the whole thing divided by 2m. Okay. So we are aware that there are three possibilities. Okay. Okay, there are three possibilities. Case number one, just to recap quickly, when you have c squared is greater than what? Greater than 4mk. When this is the case, our general solution will comprise of y as a function of t equal to c1e minus alpha minus beta and the whole thing t, and plus by c2e minus alpha plus by beta t. Okay, and we know this is basically a classification of what we call the system response as over what? Over them. So I'll write down here, anything in bracket that you see now, this is the system what? Response. And then we have to check again when case number 2, we have c squared approximately equal to 4mk. Okay, and likewise, we have our general equation, or sorry, our general solution. We have y as a function of time equal to c1 plus by c2t e minus alpha t, and this we classified it as critically damped. Okay, and finally, we have case number 3. We have c squared is less than 4mk. And then the general solution, we have y as a function of time is equal to e minus alpha t, and then we have c1 cos omega dt plus by c2 sine omega dt. And this is what we classify as underdamped. Most of the cases we are dealing with in real life are usually under there. Okay? There are some cases that you were designed for over damping, but critically damped is a very what? Fine line. Okay, it's a very fine line. Fine line means you can be critically damped, but you might have some oscillation, or you can be critically damped, you might not get any oscillation. So the two most important cases are case number 1 and case number 3. Okay. Now for this